In this topic, we'll see the classification of matrices on the basis of being real or being complex. So let's start with classification of real matrices. First one is symmetric matrix. So the definition says if a matrix being transposed is same as the original one, then it is symmetric matrix, right? So obviously for the transpose to be comparable, it needs to be of dimension with the same number of rows and columns. So it has to be is a square matrix which remains same after being transposed. Right? That is A and A transpose are same. Or you can also say Aij is same as Aji. Right? For example, if I say A is 3, 1, 5. So for Aij to be same as Aji, this has to be 3, 1, 5. If this is 1, 2, 6, so this has to be same as 1, 2, 6. And let's say this is 4, 5, 6, 4 and 5, 6, 4. Right? So if you transpose it, you'll get the same matrix, the row being changed with the column. So 3, 1, 5 becomes 3, 1, 5. 1, 2, 6 becomes 1, 2, 6. 5, 6, 4 becomes 5, 6, 4. So we will get the same thing, right? Second one is skew-symmetric. Matrix. This is the case where the transpose is exactly negative of the original, right? So obviously again for being comparable, they need to be square matrix. So is a square matrix whose transposition gives negative of the original matrix, right? That is A should be equal to minus of A transpose, or you can say Aij should be minus of Aji, right? Before giving an example, we made an observation that while we are doing the transpose, the diagonal elements remains at the same position. So A11 remains at A11, A22 remains at A22, and likewise. So if A11 is a negative of its own value, this is only possible when the value is 0. So if I am considering a 3 cross 3 matrix, first of all the diagonal matrix needs to be 0. And this is 1, this is 2. The transpose should give the negative. So this should be minus 1, this should be minus 2. If this is 4, this should be minus 4. Correct? So in this manner, 0, 1, 2 is negative, 0, minus 1, minus 2. Minus 1, 0, 4 is 1, 0, minus 4. Minus 2, minus 4, 0, 2, 4, 0. These are negative of each other. Right? So you can make a conclusion. Diagonal elements are 0. Right? The third one is orthogonal matrix. Now, a matrix is said to be orthogonal if, let's say, if for a real square matrix, the transposition is same as the inverse of it or of the matrix, right? So that means the transpose A transpose should be same as inverse of it. We'll come to the topic inverse. The understanding is if A into B gives I, B is said to be inverse of A, right? So in that manner, we understand that I'm just explaining that A into A inverse gives you I. And now that A transpose is same as A inverse, we can also say A into A transpose should give you I. What is I? I is identity matrix, and it has to be of the same size as this A or as this A transpose. Of course, it is a square matrix, right? So this is about the orthogonal matrix. Overall, we'll see some of the points about this real matrices. Let's say first one, it is any real square matrix can be written as sum of the symmetric matrix and a skew-symmetric matrix. Let's say this is A, any matrix A. Then we can write it as 1 by 2 times of A, and also 1 by A transpose minus A transpose. Of course, we can write like this because 1 by 2 times of 2A will give you A, and A transpose minus A transpose gives you 0. Now we are splitting this. 1 by 2 times of, taking 1A from here, A plus A transpose coming from here, and then 1 by A minus A transpose, right? So this A now becomes A equal to sum of a symmetric. This is a symmetric matrix. We'll see this. Let's say this is a symmetric matrix and this is a skew-symmetric matrix. I'm mentioning to be SW, right? How this is a symmetric and how this one is a skew-symmetric, we'll just see, right? Let's take an example. For any random matrix 2, 1, 3, 4, 5, 6, 0, minus 1, minus 3. Let's say this is A. Then A transpose becomes 2, 1, 3, 4, 5, 6, 0, minus 1, minus 3. So if you sum A and A transpose, you'll get 2 plus 2 is equal to 4, 1 plus 4 is equal to 5, 3 plus 0 is equal to 3. Now, before completing all the additions, let's see what I want to say. For this element, A12, it was 1 plus 4. And for A21, it is 4 plus 1. So 4 plus 1 is also 5. So 5 and 5. Diagonal elements will definitely be same. 5 plus 5 will give you 10. And let's say this also minus 6. 6 plus minus 1 is 5. So this is A23. Let's talk about A32. Minus 1 and 6 will give you again 5. This is 0 plus 3 as 3. This is A31. This is A13. So you can see this is a symmetric matrix now. Similarly, when you are doing A minus of A transpose, where you were doing the addition like 4 plus 1 and 1 plus 4, you'll be subtracting 4 minus 1 and 1 minus 4. So in this case, 4 plus 1 gives you 3, minus 1 plus 1 minus 4 will give you minus 3, exactly opposite. And what about diagonal elements? Diagonal elements are same for both A and A transpose, so it will give you all the diagonal elements to be 0. So 2 minus 2 will give you 0. Let's start with the diagonal element. 5 minus 5 will give you 0. Minus 3 minus of minus 3 will also give you 0. 1 minus 4 gives you minus 3, and 4 minus 1 gives you 3. So these are exactly opposite. 3 minus 0 will give you 3, and 0 minus 3 gives you minus 3. 6 minus of minus 1 gives you 7, and minus 1 minus of 6 gives you minus 7. So you can see that this is a symmetric matrix and this is a skew-symmetric. And of course, some of these two will give you the original matrix. All right. Now, for any two symmetric matrix, A and B, let's say A and B are symmetric, then A plus B and A minus B, both are going to be, I'll say again, symmetric. Right? Why? Because when you're doing, if A is symmetric and B is symmetric, A12 and A21 will be same, and similarly B1 and B12 and B21 will be same. So for the element of 1 2 you'll be adding A12 B12, and for 2 1 you'll be adding A21 and B21. So these two elements pairing up will give you the same result. Similarly, this applies to A minus B also. Also, AB or BA is symmetric only if AB is equal to BA, right? AB or BA is going to be symmetric only if the product of AB and BA are same, otherwise no. Also, for n to be some integer, A to the power of n is symmetric. Next point is, for any real matrix, of course square matrix, let's say A plus A transpose is symmetric and A minus A transpose is skew-symmetric. We have already seen this, but I'm just concluding, right? Let's see the next type or classification. This is classification of complex matrices. So the first one is Hermitian matrix. In short, if I'll say if A transpose conjugate is same as the A, right? This is A transpose conjugate, or I'll say A transpose conjugate, all are same, right? These two are same, is equal to the original matrix, then it'll say it is Hermitian matrix. What is the requirement? For transpose, A12 becomes A21, and for conjugate, A12 has to be the conjugate of A21. So in short, we can say element wise Aij conjugate should be same as Aji. Why? Transpose is already done. Aij and Aji are being compared, and conjugate of one should be equal to the original of that other transpose element, right? For example, if we are writing it, let's say, so before writing, let's see, if we have diagonal elements, then A11 will be transposed and will come to the same position of A11. A22 comes to the same position as to A22. Now being transpose conjugate, it has to be real, then only the conjugate part can be equal, right? So the condition is that the diagonal elements have to be purely real, and if it is off diagonal 2 plus, let's say, 3i, then this has to be 2 minus 3i. Now see, the transpose conjugate, and then so transposing will give you 4 plus 2 3i will become 4, and like let's do it. A transpose will be 4 2 plus 3i 2 minus 3i 0, and then conjugating it, A transpose ka conjugate. This gives 4 being real, 0 being real, conjugate of 2 minus 3i will become 2 plus 3i, and conjugate of 2 plus 3i becomes 2 minus 3i. So you can see, if this was A, the transpose conjugate becomes same, 4 2 3i 2 minus 3i and 0, right? So the conclusion or the point to be noted is diagonal element purely real. The second one is skew-hermitian. What is the requirement? The requirement is if the transpose conjugate is negative of the original. The transpose conjugate is negative of the original. So you can say that is like element wise, it is Aij conjugate should be minus of Aji, right? What about diagonal elements now? Diagonal elements, the the conjugate being same is only possible when it is purely imaginary or 0. Why? Because while we are transposing it, it will be on the same position. A11 remains at A11, A22 remains at A22. But if we are conjugating and then finding the value to be negative, obviously the real part has to be 0, right? So for example, it has to be, let's say, 2i, let's say 0. 0 is also a point to be considered. If it is 2 plus I, the conjugate of this should be negative of this value, right? Conjugate of this should be negative of this value. So what is conjugate of this? 2 plus I will give you 2 minus I, and negative of 2 minus I is minus 2 plus I, right? So if you want, you can try. If this is A, the transpose will become 2i 2 plus I minus 2 plus I 0, and the conjugate A transpose conjugate gives 2i becomes minus 2i, minus 2 plus I conjugate will become minus 2 minus I, this becomes 2 minus I, and this becomes 0. So you can see this is minus of 2i 2 plus I minus 2 plus I and 0. So do you see this is actually minus of A? Yes, this is minus of A. So that means this is a skew-hermitian matrix. Third one is unitary matrix. Like in case of orthogonal, A into A transpose is giving you I. Here, or otherwise I'll say A transpose was equal to A inverse. So in this case, if A transpose conjugate is same as A inverse, this is unitary matrix. So like, otherwise you can also say A into A inverse equal to I will give you, now being same, A into A transpose conjugate gives you I, right? So unitary matrix is where the transpose conjugate is same as its inverse. So A inverse gives you I. Instead of that, we can write A into A transpose conjugate giving you I. For example, let's say A being 1 plus I, 1 plus I, minus 1 plus I, and 1 minus I. You can try, do the transpose conjugate of this and then multiply with A. Then see if you are getting I. Since this is a 2 cross 2 or order being 2, you'll get second order identity matrix, right? So this is about the classification of real matrix and complex matrix.